Formation of PDE by the method of elimination of arbitrary functions. This is the second method. We shall know this method by an example. Question: form a PDE by the method of elimination of arbitrary function from the equation z equal to f of x square minus y square. Here f is the arbitrary function. We have to eliminate this f. We shall consider the given equation as 1. Now differentiate this partially with respect to x first. Okay, so dou z by dou x, we are going to represent it by small p. What is differentiation of f with respect to x? F is a function of both x and y. So f dash of x, since we are differentiating partially with respect to x, x square differentiation is 2x minus y square. Since differentiation partially with respect to x, y acts as a constant, its differentiation is 0. Just we're left with 2x. Okay, call this as equation 2. Again differentiate equation 1 partially with respect to y. So you will get dou z by dou y, which is nothing but small q again, equal to f dash of x square minus y square. Differentiation of x with respect to y is 0 and the differentiation of minus y square is minus 2y. Call it as equation 3. Now from equation 2 and 3, eliminate this f dash. How you are going to eliminate? Just by dividing these two equations, you are going to get p by q equal to f dash of x square minus y square into 2x divided by f dash of x square minus y square into minus 2y. So this f dash will get cancelled. You will just left with, again 2 also get cancelled. You will left with minus x by y. So after cross multiplication, it will be minus py equal to qx. Okay, so you can transfer here to RHS. So this is qx plus py equal to 0. This is the required partial differential equation. Okay, here no arbitrary function is there. Okay, so we shall know one more example. We will consider one more example. Form the PDE by the method of elimination of arbitrary function from z equal to f of x plus ay plus g of x minus ay. Observe here, there are two arbitrary functions. Earlier in the previous problem, there was only one arbitrary function, whereas in this problem, there are two arbitrary functions. One is f, another one is g, and we have to eliminate these two and form the PDE. Okay, and the same method, consider this as equation 1. Again differentiate equation 1 partially with respect to x, dou z by dou x, f dash of x plus ay into differentiation of this x plus ay with respect to x, you will get 1, whereas ay is 0. Again g dash of x minus ay into 1. Differentiate equation 1 partially with respect to y, f dash of x plus ay into differentiation of this x plus ay partially with respect to y, you will just get a. Again g dash of x minus ay, again differentiation of this x minus ay partially with respect to y is minus a. Just by considering these two equations, that is p and q, it's not possible to eliminate f as well as g. So we'll go for higher order partial derivatives, that is again differentiate dou z by dou x partially with respect to x again. So that is nothing but small r, dou square z by dou x square. F dash of x plus ay becomes f double dash of x plus ay into 1. Again g dash of x minus ay becomes g double dash of x minus ay. Call it as equation 2. Now differentiate this equation partially with respect to y. That is, differentiate dou z by dou y with respect to y. You will get dou square z by dou y square. As I already told you, we are going to denote this by small t. and this one is f double dash of x plus ay, again into differentiation of this x plus ay with respect to y. Already one a is there, again you will left with one more here, that becomes a square. Similarly, g double dash of x minus ay into minus a, that is minus a whole square. If you simplify this, we'll take a square, this minus a whole square becomes plus a square. Take a square common, a square into f double dash of x plus ay plus g dash of x minus ay. Okay, so from equation, observe equation 2, what you are having, it's f double dash of x plus ay plus g double dash of x minus ay, that is nothing but r. Now observe the terms inside the brackets, that is nothing but r again. So t equal to a square into r. There are no arbitrary functions, but t and r are partial derivatives. Therefore, this is the required partial differential equation.